Welcome, listener. Today we are really cracking open the strategic blueprint that defines modern electric racing. It's a detailed engineering requirement specification, or SRR, drafted specifically for the energy management system of a Formula Student electric vehicle. Our mission here is to do a deep dive into this document to understand not just the what, but, the why. Why this specific technical roadmap is the key to building a competitive car from the ground up.
That's exactly right. I mean, when you approach a challenge like Formula Student, which is fundamentally a highly constrained engineering competition, you need rigor. This SOR was built using a very rigorous methodology, the McKinsey style of MECE, or mutually exclusive, collectively exhaustive. It ensures that every single pillar, every technical requirement, every safety constraint is covered completely and without any overlap. The whole goal is to give a new university team a roadmap that's not only safe, but, actually competitive right out of the box.
Okay, so let's unpack that core strategic shift first, because for years, FSE was all about pushing for maximum performance, right? Just maximum speed. But that whole landscape has fundamentally changed.
It really has.
We know the rules now strictly limit maximum power output to 80 kilowatts. And if you look at the strategic analysis from recent competitions, like the breakdown of FSG 2025, pure peak power just isn't the differentiator anymore.
Absolutely. As a senior powertrain architect, I can tell you the game has moved on entirely. Since that 80 kilowatt power cap is a hard and fast rule, the competitive battleground, it shifted to two key areas: energy efficiency and what we call limit dynamic control. If everyone's capped at the same power, the winner is the team that can sustain that performance longer, handle the car better at the absolute limit, and, crucially, run a lighter car.
And that's exactly where the EMS, the energy management system, provides that strategic value proposition. When we talk about saving energy, we're really talking about mass reduction, aren't we?
Precisely. This is hands down the cheapest and most effective lightweighting strategy a team has. We know that effective regenerative braking can recover a really substantial amount of kinetic energy.
Yeah.
Conservative estimates start around 15%, but the top teams, they're pushing 25%, even 30% recovery over the 22-kilometer endurance event.
Wow, 30%.
Yeah. And what does that efficiency buy you? It lets you physically downsize the battery pack. We're talking about shedding 5 to 7 kilograms of accumulator mass immediately.
Wow.
And some of the really highly optimized systems, they can even push that reduction towards 12, maybe even 13 kilograms.
Wait, hold on. Cutting 12 kilograms just through smart software. Why does that weight saving matter so much beyond, a simple power to weight increase?
Because it's a systemic advantage. That mass comes off the car's total weight, which, yes, it directly and dramatically improves the power-to-weight ratio, but it also improves its lateral dynamic response. Lighter cars just corner better. They have less inertia to manage in quick transitions, and they put less stress on the entire suspension and tire system. It fundamentally transforms the car's agility, and that is where you win lap time on these tight, cone-defined FSE tracks. The EMS is the lever for competitive structural optimization.
That makes the focus of this entire deep dive incredibly high stakes then. We're focusing on two highly interdependent subsystems within this EMS. Subsystem 9.1, the regenerative braking strategy, that's the efficiency part, and 9.2, the really advanced slip ratio-based model predictive control, or MPC, braking system. That's the dynamic control part.
Right.
We have to start, like any good engineering project should, by defining the boundaries. The SOR frames Formula Student as I'm quoting here, multi-objective optimization competition under limited resources. So essentially, the rules are our boundary conditions.
The rules are the physical laws of the system we have to solve. And the single most profound boundary condition, that 80 kilowatt hard constraint, it fundamentally changes the entire optimization challenge. Let's just look at the physics for a second. Power, P equals force, F, multiplied by velocity, V.
Right.
So if P is capped at 80,000 watts, then once your vehicle gets to a medium or high velocity, the maximum longitudinal force it can generate, and therefore its acceleration, is strictly capped. And it actually diminishes as speed increases.
So if you're driving down the main straight, everyone just hits that 80 kilowatt wall eventually. No one can pull a dramatic lead through pure straight line speed.
Exactly. This forces the performance focus away from acceleration at speed and entirely onto maximizing cornering speed, so carrying more momentum through the curve and shortening the braking zone. If you can brake later and harder while keeping the car stable for turn-in, you gain time. And that puts an immense burden of responsibility right onto the EMS for dynamic stability during deceleration.
Okay, before we get into the finesse of deceleration, let's define the EMS's role. Where does the system 9.0 actually sit within the car's complex E architecture?
The EMS is the central decision-making brain. It's also important to clarify what it doesn't do.
Right.
It doesn't directly flow current to the motors. Its core function is generating the torque request. That's the highly precise command signal it sends over the CAN bus 100 times every single second, dictating exactly how much torque each of the four wheels should produce, whether that's for acceleration or for regeneration.
And to understand how it makes that request, the SOR uses this interface matrix, detailing the inputs and outputs across 4 functional layers. Let's start with the most immediate one, the driver layer.
The driver provides intent. The inputs are the accelerator pedal position sensor, or APPS, the brake pressure sensor, BPS, and the steering angle sensor, SAS. This is basically the car asking, what does the human want to do?
Mhm.
The EMS needs some pretty sophisticated logic to interpret these potentially noisy or conflicting inputs, running plausibility checks, pedal mapping. The output from this layer is the desired overall longitudinal force, $5 X, and the desired yaw rate. These are the high-level objectives.
Okay, so once the driver's intent is understood, the EMS needs to know the car's current reality. That brings us to the sensing layer.
This is all about perception. We get wheel speed from the encoders, and we get inertial data from the IMU, longitudinal and lateral acceleration, X, I, and yaw rate. But this raw data, it's not enough on its own. It's inherently noisy, and crucially, you can't calculate tire slip ratio accurately without knowing the true vehicle speed.
And that's why the SRR requires state estimation using some pretty sophisticated math.
Precisely. The EMS core must run an extended Kalman filter, EKF, or an unscented Kalman filter, UKF. A simple linear Kalman filter just won't work because vehicle dynamics are nonlinear.
Wow.
The EKF or UKF fuses that noisy IMU acceleration data with the noisy wheel speed data to output a robust, filtered, real-time estimate of the vehicle state vector, $6. This state vector includes the true vehicle speed and those all-important tire slip ratios. Without this robust estimation, dynamic limit control is frankly impossible.
That robust state estimate feeds down, but the car also has to respect its own physical limitations, which are managed in the 3rd layer, the energy layer.
Right. This is all about accumulator health. The inputs are the battery management system data, state of charge, state of health, and the critical cell temperatures. These limits are absolutely non-negotiable for safety and for the longevity of the pack.
So what's the EMS's output here? What does it do with that information?
It calculates the power limit derating coefficients, which we call kappa-bot. For example, if the cells are too hot or the state of charge is near 100%, the EMS has to calculate a coefficient that strictly limits the maximum current allowed for either regeneration or discharge. This coefficient is critical because it tells the lower dynamic layers you can optimize performance, but you cannot exceed this physical boundary.
And finally, the loop closes with the actuation layer.
Right. Here, the EMS gets motor speed and temperature feedback. It takes the driver's intent, the current vehicle state, and the energy limits, and it executes the final high-frequency control algorithms, things like torque vectoring, region blending, and slip ratio control. So the final output is that definitive set of 4-wheel torque commands, TFL, FR, RL, sent over the high-speed CAN bus to the inverters. This really shows the EMS acting as that strategic core, synthesizing driver desire, physical constraints, and optimal dynamics.
Well,
So we've defined what the EMS architecture and the interfaces. The next logical hurdle for any new team is, well, the how. How do you actually build this incredibly complex system reliably and safely in a compressed 9 to 12-month timeline while also trying to implement cutting-edge stuff like MPC?
That challenge immediately brings us to Section 2, Controller Architecture and Strategic Tooling Selection. The SR outlines 3 strategic technical pathways to manage the risk. First, and this is mandatory, is adherence to the V-model development process.
The V model is just non-negotiable for safety-critical systems, especially in FSE. It mandates a really rigorous verification flow. You start with requirements on the left side of the V, move through design, and then you have to verify each stage on the right side. Model in the loop, hardware in the loop, and finally, physical testing. This structure prevents what we call late-stage chaos, finding a fundamental flaw during physical testing that you really should have caught back in the design phase.
Can you give us a quick anecdote? What happens when a team tries to skip the V model?
Oh, absolutely. I once consulted with a team that felt they were too time-constrained to build a proper a hardware-in-the-loop setup. They went straight from a MIL-L simulation to the physical car. On their first high-power test run, a minor bug in the torque vectoring logic, something that would have been a non-issue in simulation, it caused an unexpected torque spike. The resulting shock loaded the drivetrain so severely that it shattered the gearbox casing.
Oh.
Yeah. They lost 2 weeks of testing and had a 5-figure replacement bill. The V model front-loads that verification to avoid these catastrophic, expensive, and time-consuming failures.
That perfectly justifies the rigor. Okay, pathway 2 is the hierarchical control architecture.
This is the software's own safeguard. We have to segment the vehicle control unit software into 3 prioritized layers: safety monitoring, energy management, and dynamic execution. The crucial design principle here is priority. The safety monitoring layer, which handles things like thermal shutdowns and BSPD logic, it has to run independently and always have the highest priority. If a safety fault occurs, it must override and zero out any performance-driven torque requests from the dynamic execution layer instantly.
And pathway 3 addresses efficiency in development, model-based design, or MBD.
MBD is the modern team's secret weapon. By using tools like MathWorks, Simulink, and Stateflow, the team can focus 80% of its effort on developing the control logic visually, right in the model, rather than sinking weeks into writing, debugging, and verifying low-level C code. The software can automatically generate verified C code. It dramatically accelerates the path from requirement to deployable code and helps you escape that swamp of low-level driver development that really plagues novice teams.
Which leads us to a critical decision point, the controller selection strategy in SR 3.1.1. If model-based design is the goal, what hardware actually supports it best? We see the trade-offs laid out: high-cost industrial solutions versus low-cost microcontrollers.
This is a classic strategic trade-off analysis. On one end, you have industrial rapid control prototyping systems like the D-Space MicroAutobox 3. It's got high compute power, incredibly high development efficiency, but a high cost. On the other end, you have the low-cost microcontroller like an STM32H7 medium compute, mid-level development efficiency, and very low cost.
So for a new team on a tight university budget, the temptation is always to pick the STM32 because it costs, what, less than 50 euros? Why does the SOR strongly advise against this for a first-year team?
Because the total cost of ownership is defined not by the hardware price, but by the engineering hours it takes to make it work. A new team just lacks that deep embedded systems expertise. By choosing something like D-Space, they buy a fully validated, production-ready system where the embedded code generation, the sensor drivers, the CAN stack, it's all guaranteed to work out of the box. The key recommendation here is strategic. Use RCP systems like D-Space to focus 80% of your engineering effort on solving the control strategy problem, which is your competitive core, rather than solving the embedded hardware interface problem.
That's a powerful justification. It's an investment in speed and reliability so the team can focus on the IP they're actually trying to generate.
Exactly. Now, if the cost truly is prohibitive, the STM32H7 is the next best option, but only because it has robust support for MathWorks embedded coder, which keeps MBD viable, but it will take more effort on the integration side.
Now, let's look at the nervous system of the car. The communication topology and sensing, which have to be flawless for any kind of dynamic control.
Right. For slip ratio control, high bandwidth and ultra-low latency are paramount. Our sensing has to be precise. The SOR explicitly details the wheel speed requirement. You cannot use simple Hall sensors. You need high-resolution encoders, preferably a resolver or a high-precision magnetic encoder, like a 14-bit AS547.
Why are Hall sensors insufficient for this? What's the problem?
A typical Hall sensor gives you maybe 4 to 8 pulses per revolution. At low speed, that resolution is just far too coarse. If you're calculating slip ratio, a smooth, high-frequency signal is essential. Low-resolution signals generate significant noise when you try to derive a slip ratio estimate, especially during braking. A noisy slip signal means your complex MPC controller, which is trying to precisely adjust torque, will get unstable inputs and will inevitably start to oscillate or fail to converge. That leads to dangerous control instability. High resolution is a requirement for high performance.
And that high-resolution data needs a clear channel to travel on. The SOR mandates segmenting the network using 2 CAN FD buses.
Network segmentation is critical for maintaining deterministic latency. CAN 1, Powertrain, must run at 1 Mbps, the highest bandwidth, and is reserved solely for time-sensitive, safety-critical data. The 4-wheel torque commands, inverter feedback, and safety system status. CAN 2, vehicle, runs at 500 kilobps and carries all the non-critical data, logging, telemetry, dashboard info, that kind of thing. By isolating the high-frequency control loop onto its own bus, we guarantee that those crucial torque commands are never delayed by a burst of telemetry data.
So before any team even thinks about tuning the car for speed, they have to get their license to race. Section 3 addresses the unbreakable safety barrier, the regulatory compliance that forms the foundation of the entire system.
In the world of competitive EV design, compliance isn't just bureaucracy, it's a hard engineering constraint. A single failure here, and you're disqualified. Let's start with one of the most mechanically demanding rules, the brake over travel switch, or BOTS, mandated by Rule EV 5.5.
Explain the purpose of BOTS. What's it for?
It's the mechanical failsafe for a hydraulic failure. The rule requires a mechanical switch to cut the shutdown circuit if the driver presses the brake pedal past its normal travel limit. That signifies a catastrophic failure, like a completely blown brake line. The objective is to immediately disable the 80 kilowatt power source if the primary mechanical braking system can't function.
And the SRR goes into a lot of detail on the mechanical design requirements in 4.1.1, dictating a two-stage travel pedal assembly. What does that actually mean for the mechanical engineers on the team?
It means the pedal structure has to be engineered with two distinct zones of travel. Stage A is your normal operating travel, from 0 up to the point where the master cylinder pistons reach their limit and the hydraulic pressure should be max. We call that 6 lock. Stage B, the fault over travel, is the extension from that point to the mechanical stop. This Stage B space must be large enough to physically accommodate the BOTS mechanism, and the only time the pedal should ever enter it is under a severe fault condition.
And why is that physical mechanical switch requirement so important? Why can't software do it?
It has to be an independent hardware fault mechanism. It's typically a normally closed mechanical switch, which means it requires zero power to maintain its integrity. If the switch is physically opened by the pedal entering Stage B, it breaks the safety circuit. And crucially, the SOR stresses that software logic must not trigger BOTS. This rule is about independent physical protection, not software interpretation.
You mentioned scrutineering tests earlier. How does the team prove to the judges that their BOTS actually works?
This is a high-stakes moment during static scrutineering. The team has to demonstrate the BOTS functionality by simulating a hydraulic failure. The common method is to open a caliper bleed screw on the hydraulic system, which effectively drains the fluid path. The driver then applies maximum force. The pedal has to sink past normal travel, physically engage the BOTS switch, and the team must verify that the tractive system shuts down immediately. If the pedal structure bends or breaks or deforms before the BOTS activates, the design fails. Rigidity is safety.
Okay, next we move from structural safety to power regulation. The 80 kilowatt power limit control, Rule EV 4.1, this is where software prevents immediate disqualification from the endurance event.
Yeah, and this is a complex control problem because of the latency issue. The VCU has to implement predictive power limiting. You can't just wait for the external official energy meter to report a violation and then react, because that meter has inherent latency. By the time you react, the violation has already happened, and you're disqualified.
So the VCU has to be constantly anticipating and calculating.
Precisely. The control strategy has to use its own high-frequency internal current and voltage measurements to run a PID controller targeting a maximum power output of maybe 78 to 79 kilowatt. That 1 to 2 kilowatt safety margin is the absolute minimum buffer you need to account for noise, sensor tolerances, and any minor control lag. And the control loop frequency has to be extremely fast, at least 100 Hertz. Why? Because aggressive acceleration can cause these rapid current spikes. A flow control loop won't catch those spikes in time to prevent a momentary disqualifying overshoot.
And of course, the dual pedal safety checks, the plausibility checks, APPS, BPS, Rule EV 2.3. What's the driver intent safety logic here?
This rule targets driver confusion or sensor failure. If the driver is standing on the brake pedal and simultaneously commanding significant acceleration, so the accelerator pedal is over 25%, the system has to assume there's a fault. The EMS must force motor torque to 0 and do it within a critical window of 100 milliseconds. This stops the car from driving against the brakes, which can lead to high current draws, thermal events, and uncontrolled acceleration.
Finally, we hit the ultimate independent hardware layer, the brake system plausibility device, or BSPD.
The BSPD is the last line of physical defense. It's defined as a non-programmable independent hardware safety circuit. It triggers only when two conditions are met at the same time. Hard braking, so hydraulic pressure, typically over 30 bar ND, the motor consuming or generating over 5 kilowatts of power.
That power threshold seems incredibly low. 5 kilowatts. Why such a small number?
That 5 kilowatt threshold is designed to catch scenarios where the motor is actively driving the car while the driver is trying to emergency brake. But here's the critical nuance for an efficient EV. Heavy regeneration also generates power. It generates negative power flowing back into the battery. If a team designs a BSPD circuit improperly, the negative power generated during heavy controlled regeneration could erroneously trip the BSPD because it just detects the absolute value of the power flow exceeding 5 kilowatt.
So the team needs a really smart circuit design to prevent the BSPD from triggering when the car is safely regenerating, which is exactly what you wanted to do during braking.
Absolutely. The design has to precisely distinguish between positive power-consuming power from the battery and negative power, regenerating power into the battery during hard braking. The rule targets power consumption. The team must ensure their independent hardware circuit uses directional current sensing or polarity checks to only trigger the error cutoff if the current is flowing out of the accumulator while the brakes are on. Failing this circuit design means unnecessary shutdowns during the endurance race, which are just disastrous for your lap time and reliability. With safety established, we can transition directly into performance enhancement. Section 4 is Subsystem 9.1, Advanced Regenerative Braking Strategy. This is where we maximize energy recovery, but we always have to subordinate that recovery objective to the absolute requirement for vehicle stability.
The physics of blending hydraulic and regenerative braking are fundamentally complicated by dynamic load transfer during deceleration.
This is the danger zone. Total braking force is the sum of hydraulic and regen forces. Formula student cars are typically RWD, or at least use regeneration primarily on the rear-driven axle. When you brake aggressively, inertia causes longitudinal load transfer, but weight pitches forward. This severely reduces the rear vertical load available for grip. If the EMS commands too much regenerative torque to those rear wheels, that lightened rear axle can easily exceed its maximum friction and lock up before the front wheels.
Which results in a classic snap-oversteer moment and probably a spin.
Correct. A spin is an immediate fail in any dynamic event. The EMS has to manage this with extreme precision. The SOR recommends a series brake blending strategy detailed in 5.1.1 because it offers the highest efficiency potential while maintaining a consistent pedal feel for the driver.
Let's break down that series blending strategy, starting with light braking. What does that look like?
Light braking is defined as low deceleration, typically 0 to 0.3 G. This covers minor speed adjustments, corner entry braking. In this phase, the system should prioritize energy recovery entirely. Only the rear axle motors provide the regen force. The hydraulic system might be monitored, but the calipers aren't actively clamping. The driver feels the pedal pressure, but all the braking force is electric.
Then we hit heavy braking, anything above 0.3 G.
This is the safety and high-performance zone. Here, the hydraulic brakes must intervene to satisfy the total required braking force. The VCU takes over the blending. It commands the maximum safe regenerative torque, critically limited by the estimated rear wheel slip ratio to prevent lockup, and then the hydraulic system is commanded to cover the remaining force shortfall. This requires a precise dynamic mapping function, something like turgid equals a function of pressure, speed, and SOC, constantly adjusting regen based on driver intent, current speed, and of course, battery limits.
That seamless blending hinges entirely on the battery's ability to accept charge, which brings us back to those battery derating maps in SOR 5.2.1. This isn't optional, it's a necessary constraint, right?
It protects the $500,000 battery pack from permanent damage. If we ignore the battery's charge acceptance limits governed by state of charge and temperature, we risk severe degradation, particularly lithium plating. The VCU has to implement precise multidimensional lookup tables to calculate the maximum allowed regen power.
So let's look at the specific SOC derating limit.
Okay. Below 80% state of charge, we typically allow 100% of the available regenerative power, assuming the temperatures are good. The danger zone is between 80% and 95%. In this range, the EMS must enforce a strict linear reduction, tapering regeneration down to 0. Above 95% SOC, regeneration is strictly forbidden. Trying to force charge into an almost full cell leads to high internal resistance and a severe risk of plating.
And the temperature constraints are equally rigid. The temperature derating map is a hard safety feature.
Absolutely. If the cell temperature drops below 10 degrees Celsius, regeneration is strictly forbidden. Low temperatures dramatically increase the risk of lithium plating because the kinetics of intercalation slow right down. This is irreversible damage. The ideal operating band is between 10 and 45 degrees Celsius. If the cells heat up beyond 45, the VCU has to start a linear power reduction, cutting out all regeneration completely if a cell hits 60. The EMS even has to predict the state of charge for the entire race, preemptively derating capacity if the battery model suggests the pack will peak above 95% mid-race.
And if the regen strategy is successful, it offers more than just recovered energy. It has significant thermal and mechanical benefits.
This is the full systemic advantage. Traditional FSE cars, relying heavily on mechanical friction, can see brake disc temperatures soar past 400 degrees Celsius during dynamic events. This heat causes fade, increases pedal travel. It's a major safety risk. Effective regeneration, which handles the majority of those low J braking events, acts as a heat mitigant. We can reduce peak disc temperatures by over 20%, bringing them down to a much safer 320-degree range.
A 20% reduction in thermal load. That must give the mechanical engineers a lot more flexibility.
It does. It allows them to specify smaller, lighter brake components, smaller discs, smaller calipers. This directly reduces unsprung mass. And unsprung mass is critical. It's the mass below the suspension springs. Reducing it improves the natural frequency and responsiveness of the suspension, which allows the tires to maintain better contact with the road over bumps. That translates directly into better mechanical grip and better dynamic performance.
We also can't forget the motor itself has physical limitations. SRR 5.3.1 details the motor constraints.
Yes. The VCU's regen torque command has to always respect the motor's instantaneous torque speed envelope. Electric motors enter a state called field weakening at high rotational speeds. This causes the maximum available torque, whether you're driving or regenerating, to drop steeply. If the control system commands 50 Nm of regeneration at a speed where the motor can only physically deliver 30 Nm, the control integrator will saturate or wind up. This can lead to system instability and control failures when the driver transitions back to acceleration. Direction must always be a constrained output.
Now we're moving into the domain of dynamic performance and some really cutting-edge software. We're in Section 5, Subsystem 9.2, Slip Ratio-Based Model Predictive Control, MPC. This is the key technology that allows the team to push the physical limits of the tire.
This is truly where that strategic investment in MBD and high-speed hardware pays off. Why MPC? Because the challenge of maximizing braking force is a constrained, multivariable, nonlinear optimization problem. We need to decide the optimal torque for 4 different wheels, constrained by the driver's pedal pressure, the road friction, the load transfer, the battery limits, all in real time. MPC is designed specifically to solve this kind of optimization.
And the ultimate goal is maximizing that longitudinal force, $5, which is described by the Pashejka magic formula. It relates force to slip ratio. Where is that sweet spot?
On dry asphalt, the peak grip region, where the tire is generating its maximum braking force, occurs when the wheel is slipping relative to the road speed by about -10% to -15%. If the slip is less negative, you're underutilizing the tire. If the slip exceeds that, say, -20% or -30%, you're skidding, generating tire wear, and critically, the force curve drops off dramatically. The MPC's core mission is to keep the wheel speed locked onto that small, optimal band.
But as we discussed in the interface matrix, none of this works without a rock-solid calculation of that slip ratio. That brings us back to the prerequisite, state estimation using Kalman filters.
Absolutely non-negotiable. Because all 4 wheels are slipping during braking, you can't just average the wheel speeds to get true vehicle speed. If your speed estimate is off by 5%, your slip ratio calculation is junk and the MPC will fail. That's why the SOR mandates the extended Kalman filter, EKF, or the unscented Kalman filter, UKF.
So how does the EKM solve this fundamental problem?
It fuses the short-term accurate IMU acceleration data with the long-term integrated wheel speed data. The EKF runs a mathematical model of the vehicle and compares its prediction to the sensor inputs. If the model is correct, the EKF provides a powerful filtered estimate of the vehicle state. Crucially, it doesn't just filter noise. It can estimate unknown parameters like the IMU's inherent acceleration bias or even estimate the current coefficient of friction on the road. This makes the whole state estimate robust against sensor failures and varying track conditions.
Once that reliable state vector is in place, we can model the MPC controller. What does the prediction model actually look like inside the VCU?
Well, it has to be simple enough to run in real time. We typically use a simplified single wheel or quarter car model. The model predicts the state of the wheel over the next few time steps based on the current state, the motor torque, and the predicted tire force, which is a function of slip ratio. The model doesn't need to be perfect, but it has to be fast and representative of the key dynamics.
And the MPC seeks to minimize error through its cost function, which is structured as a quadratic programming problem. Let's explore the 3 cost terms that define how the controller behaves.
The cost function defines the controller's personality, so to speak. The solver calculates the future sequence of torque commands that will minimize this total cost.
Okay, so term 1 is tracking.
This is the performance term. We're minimizing the slip ratio error. The weight matrix, Q dollars, determines how much we penalize deviations from the optimal slip ratio. If Q dollars is large, the controller is aggressive. It prioritizes getting back to that negative 12% slip immediately, even if it requires large, rapid torque changes.
Term 2. Control effort.
This is the stability term. It penalizes the rate of change of the torque command. If the weight, $3, is small, the controller can be twitchy and noisy. If $4 is large, the controller commands smoother, slower changes in torque. This is essential for protecting the drivetrain, preventing vibrations from shattering half shafts, and for ensuring good driver feel. You don't want the brake pedal buzzing constantly.
And the third term, soft constraints.
Right. MBC solves optimization subject to hard constraints, like the 80 kilowatt limit. But sometimes, if constraints conflict due to sudden changes, the solver might fail to find a solution, which would crash the control loop. The slack variable term introduces a penalty for constraint violation, allowing the solver to find a slightly suboptimal, but guaranteed, feasible solution. This is essential for robustness in real-world racing.
So this means that parameter tuning, adjusting those Q and R weights, is where the art meets the science, and that has to be done during HL testing.
It is the calibration phase. You must have distinct tuning maps. For a high-grip dry track, you want a relatively large Q-aggressive tracking, because the risk of instability is lower. However, if the track is wet, the optimal slip ratio shifts, the friction curve is shallower. You have to massively increase the R weight, prioritizing smoothness and stability, and potentially reduce Q. If you use dry tuning on a wet surface, the car will constantly overslip and fail to maintain control. Tuning is literally defining the limits of the car's grip for different environments.
Finally, there's the computational hurdle, the embedded solver implementation. MPC needs to solve a QP optimization problem every 10 milliseconds. How do we ensure that happens on the flight hardware?
This is where we pay attention to toolchain optimization. The SOR recommends OSQP operator splitting quadratic program, or QP-OACs. OSQP is highly recommended for embedded systems because it's designed to generate highly optimized, library-free C code. This eliminates dependency on complex external libraries.
And you mentioned a key feature called warm start.
Warm start is vital for speed. Since the vehicle state changes only slightly between 10 millisecond control cycles, the optimal solution at time J2 is usually very close to the optimal solution at time K1. Warm start uses the previous solution as the initial guess for the current step's optimization. This drastically reduces the number of iterations the solver needs to converge. If we're running an STM32H7, a 480 MHz chip, the solver must reliably converge within 2 to 3 milliseconds to meet that 100 Hz control frequency target. OSQP with warm start makes this aggressive timing possible. Developing a system that integrates safety, energy efficiency, and dynamic control is inherently risky. So Section 6 focuses on verification, validation, and testing the V&V roadmap, which is essential to de-risk the entire project timeline.
And we start with Phase 1, model-in-the-loop MIL simulation. This is the proving ground for the pure control logic itself.
In MIL, we build a comprehensive vehicle plant model, the digital twin and Simulink. This includes detailed models of the battery, motors, tires, and the entire vehicle mass and inertia properties. The test goal is primarily sensitivity analysis, checking how robust the control system is to variations in vehicle parameters and accurately predicting the energy recovery rate. Our key target metric in simulation is aggressive. We want to achieve a validated 5–10% shorter braking distance compared to pure hydraulic-only braking, and verify that all the safety-critical regen logic works flawlessly without violating any limits.
Phase 2 dramatically increases the fidelity and is where you catch those hardware-software integration problems. Hardware-in-the-loop, HIL testing.
HIL is where we mitigate 90% of the risk before the car ever moves. We connect the actual VCU, the D-space or STM32 box running the generated C code, to a real-time simulator, which feeds it synthetic sensor data and mathematically models the car's reaction. We're testing the actual code on the actual hardware.
And the most critical HIL procedure, which you cannot skip, is fault injection.
Absolutely. This is the difference between passing and failing safety scrutineering. The team has to proactively simulate catastrophic failures, a sudden loss of a wheel speed sensor signal, the CAN bus failing, or the battery thermal sensor reading an over-temperature event. The test verifies that the VCU correctly executes its safe degradation modes, or safe state, by immediately limiting power or triggering a shutdown rather than just continuing to drive.
What are the key performance metrics you measure during HIL?
We measure latency and reliability. The HIL verifies that the total system latency, from the brake pressure sensor input on the VCU pin to the final torque command output on the CAN bus, is reliably less than 15 milliseconds. It also confirms the MPC solver execution time is reliably less than 5 milliseconds on the flight hardware. If these timing constraints are violated in HIL, the team knows they have to optimize the code or upgrade the hardware before they ever hit the track.
And finally, we get to phase 3, on-track testing, the real-world validation. It starts static, right?
Static checks confirm the basic compliance items that require physical hardware interaction. Verifying the BOTS triggers correctly with the physical pedal assembly and confirming the ready-to-drive sound sequence is correct. Then we get dynamic.
What are the dynamic tests specifically designed to validate this advanced EMS?
First, straight-line emergency braking runs, typically from 30 up to 70 kilometers per hour. This is pure longitudinal testing to empirically calibrate the optimal longitudinal slip ratio targets. Simulation gives you the starting point, but real-world tire dynamics are always slightly different. Second, and more challenging, are the brake-in-turn tests. This validates the MPC stability under combined longitudinal and lateral load. Since the car is turning, the weight distribution and tire slip budget are constantly changing. The team adjusts the trevor weight in the MPC, the weight responsible for yaw rate tracking, to ensure that the braking doesn't induce instability or cause the rear end to step out.
And the final, ultimate proof point.
The 22-kilometer endurance simulation. Running continuously verifies the long-term system health. This is the only way to validate the accuracy of the battery thermal model, ensuring the derating strategy holds up under continuous high-power cycling and heat buildup. If the thermal model is wrong, the battery will aggressively limit power halfway through the race, rendering the entire efficiency objective completely useless.
This has been an incredibly detailed look at how compliance and performance are engineered in a modern FSE vehicle. So as the strategic consultant guiding this new team, what are the 3 overarching high-level takeaways they absolutely must internalize from this?
Well, the SOR provides a clear 3-pillared path from compliance all the way to competition victory.
Pillar 1, compliance is foundation.
The safety rules are non-negotiable hard constraints. If your mechanical engineers fail the BOTS design, or your control engineers fail the 80-kilowatt limit, the car simply does not race. All the complex performance strategies, the MPC, the regen blending, they all have to be nested safely inside these regulatory boundaries. Safety is the strategic entry ticket.
Pillar 2, efficiency is competitiveness.
This defines the mission's strategic target. The goal isn't peak power, it's 20% plus energy recovery and endurance. This translates directly and powerfully into a massive, advantageous reduction in battery mass, which fundamentally improves the vehicle's dynamic capabilities in cornering. Smart software is the ultimate lightweighting strategy.
And pillar 3, which is essential for timeline management, control must be phased.
For a first-year team, over-ambition is the greatest killer of race day dreams. The advice is to secure a reliable, safe system first. Start with a robust, rule-based control system and a safe, achievable parallel region system. Focus on successful scrutineering and gathering crucial data. Only after accumulating a full season of data and robust HIL validation should the team even attempt the advanced complex strategies like series blending and MPC slip ratio control in year 2. You have to master the basics before pushing the limits.
That phased approach makes the immediate next actions for the team crystal clear. It gives them direction starting tomorrow.
Absolutely. Their immediate priority is securing the necessary development hardware, the D-Space RCP unit or the STM32H7, to start that model-based design flow. Concurrently, the mechanical subteam must finalize the brake pedal assembly design, specifically engineering in that 2-stage travel required for the BOTS mechanism. And most importantly, they need to establish the comprehensive MATLAB Simulink simulation environment to begin those initial MIL-NL simulations and parameter sensitivity analyses.
It's just so clear that in modern FSE, victory doesn't go to the team with the largest budget or the biggest motors. It goes to the team with the most disciplined engineering process.
That's the competitive edge. This deep dive proves that the best energy management system isn't about having the largest battery pack. It's about having the safest, smartest, and most robust control logic managing every single millisecond of the race. The intelligence in the VCU is the key differentiator.
A perfect articulation of the modern racing strategy.